Okay. In this problem, we're going to find V0 using nodal analysis. We're using our problem-solving strategy on nodal analysis. And if you'll refer to the problem-solving strategy, the first step is determine the number of nodes in the circuit. So if we look, 1, 2, 3, and then the node at the bottom. So now we have 4 nodes. Okay, we're going to pick one as a reference node. Let's pick the bottom one. Okay, and now let's assign a node voltage. And I'm going to call this one V1, this one V2, and this one V0. Again, remember the polarities that we have for our node voltages. So we have 4 nodes, 3 node voltages. Okay. And those node voltages are V1, V2, and V0, which means we have to have 3 equations. Now, this time we have a voltage source which is connected to 2 non-reference nodes, and if you remember, that means that we have a supernode. And if you look at our problem-solving strategy, we write a constraint equation for every voltage source. So one of our 3 equations will be a constraint equation. So we're going to use KVL to get our constraint equation. And we'll use KVL around this loop. So when we do that, if we start here and go around, we'll have minus 12 plus V2 minus V1 equal to 0. So the constraint equation is V2 minus V1 equal to 12. So there's one of our 3 equations. Now we need to get 2 other equations. And if you look at our problem-solving strategy, we'll go in and apply KCL at this node, and then we're going to have to go in and apply KCL at the supernode. Okay, so again, our circuit, let's put the node voltages on here. Reference node. Here's our supernode. Okay, so now let's go in and apply KCL at this node. So we'll have V0 over 1K plus V0 minus V2 over 2K. And that's equal to 0.002. So this first term is the current leaving here. This term is the current leaving here. And then we have 2 milliamps entering. Okay, so this can be rewritten as follows. Okay, so there's our second equation. Now we need to do KCL at the supernode. Okay, and what we'll do is less some currents leaving the supernode through these resistances and set it equal to the sum of currents entering from sources. So we'll have, for instance, here we'll have V1 over 3K. Then this current will have V2 over 6K. And then this current will be V2 minus V0 over 2K. Okay, there's the current leaving through those resistances. Now currents entering from sources will have 0.008, which is that current. And then we'll have a current of 0.002 leaving. So that'll give us 0.006. And then if we collect up terms, we'll have 1 over 3K times V1, 1 over 6K plus 1 over 2K times V2, minus 1 over 2k times V0 is equal to 0.006. Here's our third equation. So now we're ready to put them in a matrix and solve them using MATLAB. So our three equations in. First we'll put the constraint equation. It doesn't make any difference what order you put the equations in. So there's the constraint equation. Here's our second equation. And then here's our last equation. This one's the KCL at the supernode. Now, in matrix form, we can solve them using MATLAB. So we get V1 is 0.8 volts, V2 is 12.8 volts, and V0 is 5.6.